Hello, and thank you for joining me today as we begin our discussion on nuclear chemistry. So this is going to be a kind of a short unit as far as this class goes. We don't go into too much detail, too much depth, but we're going to talk about nuclear chemistry and its applications and how we use it in our daily lives. So let's get started. So section 1, we're going to talk about what's called nuclide notation. So a nuclide is any radioactive nucleus, or a nucleus in general is a nuclide. And we're going to talk about what's called the band of stability. So at the end of this lesson, you'll be able to utilize nuclide notation to obtain information, which you've done already. We just give it a different term. So you're going to do that again, and then we're going to look at the importance of what's known as electrostatic forces, or electromagnetic forces, and the strong nuclear force on a nucleus. We'll talk about both of those. And last but not least, we have this thing called the band of stability. We're going to talk about what that means and what we can understand about atoms that fall above and below this band of stability. So here we go. To start with, nuclear chemistry, we talk about what's called a nucleon. So a nucleon is a term for any subatomic particle found in the nucleus. So if you think back, we know that there are two particles found in the nucleus. Those are protons and electrons. So any proton, or protons and neutrons, I apologize. Protons and neutrons are found in the nucleus, and so those are our nucleons. That being said, our nucleon number is going to be the same as our mass number, because we know that protons have a mass of 1 AMU, and neutrons also have a mass of 1 AMU. Electrons had a mass of 0. So our nucleon number and our mass number are the same thing, because both particles with a mass are found in the nucleus. And then a nuclide, or a nuclide, is any specific atom. For example, carbon 14, oxygen 16, all of those are nuclides. So question, how many protons and neutrons would a nitrogen 14 nuclide have? So looking at this, you know you have nitrogen. If you have nitrogen, you can look at your periodic table and you know that nitrogen has an atomic number of 7, which means that it's got 7 protons. If the mass, which is given here, is 14, mass number is protons plus neutrons. So 14 minus 7 means I have 7 neutrons as well. So you've done this, but this is nuclide notation, which is what you've done already. So here we go. A nuclide that has 26 protons and 33 neutrons is used to study blood chemistry. What are the two ways I can write this nuclide? So first, what is this element? So I have 26 protons. Check your periodic tables. We know that 26 protons means the atomic number is 26. And if I look at the periodic table, my number, atomic number 26 indicates it's iron. So I have iron, and then 26 plus 33 is 59. Is 59. So I have iron 59, or I can write that as 59 Fe. It's not mandatory that you write this 26 here, because I told you it's iron. Iron's number on the bottom is always 26. Either one of those work. Or you can write it as Fe59. I'll let you try these next two on your own. You can pause the video, try those quick. When you resume, I will give you the answers. So there's your iron 59s. The second nuclide in radiation therapy for cancer treatment has 39 protons and 51 neutrons. Express this in two different ways. So because it's got 39 protons, we know it's strontium. So this is strontium 90. So I can write it like so. Or I can write SR-90, or I can write it out strontium 90. The last one, a nuclide with the symbol of 201 TL, can be used to assess a patient's heart in a stress test. Find the atomic number, mass number, protons, neutrons, and express it in two different ways. So atomic number 81, because it's TL, this is thallium. Atomic number is 81. Because it's 81, I have 81 protons. My mass number is given here. So mass is 201. To find neutrons, 201 minus 81 gives me 120. And I can write as your thallium 201, TL 201, or I could write it like this, but they gave that to you already. So there is your practice. All right. When we talk about atoms, we talk about the nucleus. There are two forces that hold or that act on a nucleus. The first one is the thing that holds it together. Because if you think about what's in a nucleus, you have protons and you have neutrons. Now, thinking about this, protons have a positive charge. Neutrons have no charge, they are neutral. What do we know about two things that have the same charges? If you have the like charges, you repel each other. That means these protons want to push against each other. So the idea that two protons can be within this close of proximity is kind of absurd. And so what holds them together is known as a strong nuclear force. This is the force exerted by neutrons that holds this whole shebang together. There's a whole bunch of energy that goes into holding all of this together. So this is one force, is your strong nuclear force. The other one is your electromagnetic or your electrostatic forces. These are forces between positive and negative charges. So the fact that the protons want to push apart is this electromagnetic force. And the electrons pulling from the outside is an electromagnetic force. So the electromagnetic makes the protons want to go this way, and your strong nuclear force holds those together to create what we know as the nucleus. The protons are positive, they repel each other. Neutrons act like the glue, and they buffer the charges and hold them together. And that's how this all stays in one piece. We're going to look at this proton to neutron ratio because this is really important when we talk about nuclear or radioactive nuclei and nuclides in general. So if we look at the proton to neutron ratio for the most abundant and typically the most stable isotopes of your elements. So nitrogen has 7 protons and 7 neutrons, which is a 1-to-1 ratio. So I have 1 proton to 1 neutron. As I get bigger, as I go down in this column 15, group 15, below that's phosphorus. Has 15 protons, 16 neutrons. So 1.07 to 1 neutron to proton ratio. Arsenic has 33 protons and 42 neutrons, 1.27 to 1 ratio. As I get bigger, antimony is 51 to 70, 70 to 51, which is 1.31 or 1.37 to 1, and bismuth is 83 and 126, so 126 to 83, which is 1.52 to 1. These are stable isotopes. So if you do this for all of your elements and not just column 15, you create what's known as this band of stability. You can notice this band of stability. And so this red line here is indicating a 1-to-1 proton to neutron ratio. So if it was a 1-to-1 ratio all the way up, we would go this way. But as you get bigger, specifically as you get really bigger than 20, anything above 20 starts to go a little bit more than 1-to-1. And the bigger you get, the more buffers you need, the larger your ratio gets. This is known as our band of stability, meaning that nuclides that fall in this range, in this region, typically tend to be more stable. Typically tend to be more stable. If you fall above here, for example, if I have an element, an atom that's got 30 protons and let's call it 60 neutrons. If I fall right here, I'm not in this band of stability. I have too many neutrons, so it's going to undergo decay to fall back into this range. Now, if it's got 30 protons, it wants to have somewhere around 40 neutrons, give or take a couple. Okay, that's going to give you your more stable configuration. But this is a band of stability which gives an indication to what kind of decay an atom is going to undergo to become stable. And we'll talk more about that in the next section. But your band of stability is the neutron to proton ratio in which a nucleus is stable or most stable. So if a nucleus falls within this band, this range, it is typically not radioactive. It's stable, it's going to hold it's going to maintain, it's not going to break down, it's not going to lose protons or gain neutrons or anything like that. If it's outside of this band, it's what we consider radioactive, meaning it is going to it falls outside of that range, so it's going to break down. It's going to try to get back to this range of stability. And it does that by what we call radioactive decay. This is releasing emissions to change the nucleus to a stable ratio, stable neutron to proton ratio. We'll talk about this process in the next little section. But if it falls outside of this range, it's going to try to get back in there. And so you see this section here has been blown up. The blue band is the stable configuration. Anything blue in this little chart is stable. If it's above that, we have too many neutrons. Our neutrons is too many. So it's going to undergo what we call beta emission. We're going to talk about this later. But anything up here is going to undergo beta decay, because that is going to eliminate the number of neutrons, or reduce the number of neutrons, and increase the number of protons. So it's going to help it fall in this range. If it's below here, if it's slightly below this range, so in this light yellow section, it's going to undergo what we call positron emission or electron capture, which increases your proton number, or let's see, it decreases your proton number while increasing your neutron number, is what these do. And we'll talk about this, like I said, we'll talk about this in the next unit, but this decreases protons and increases neutrons. If it's way outside of that, so these ones down here that have a long way to go, this undergoes what we call alpha emission, which reduces your proton number without changing, reduces both of them actually, protons and neutrons down here. We'll talk about that. All right, nuclear reactions. These are, we use this with for energy purposes, but this involves changes to the nucleus, whereas chemical reactions involve electrons. So anything nuclear is looking at changes to a nucleus. So all of your nuclear reactions involve changing your protons and neutrons. If we're talking chemical reactions, which is what most of this course is going to be based on, we're dealing with electrons. So for now we're talking protons and neutrons. The rest of the year we're going to talk about electrons. An important part of nuclear chemistry is the rate of your nuclear reaction is unaffected by temperature, pressure, or the presence of other atoms. So you can't really add a catalyst to these reactions. They just take place. Whether you cool them down or heat them up does not really matter. The reaction is going to take place at the same time, in the same amount of time. Same with pressure. You increase or decrease the pressure, not going to change your nuclear reaction. All of that's going to remain constant. All right, here's some questions for you to answer. Make sure you can do these or look these over before you come back to class. If you have questions, please let me know. But read these through, check these out, and then I look forward to working with you through the rest of this unit. Thank you for your time and enjoy the rest of your day.